This video is about adding, subtracting, and dividing radical expressions. To get started, we have to understand a basic idea, which is this. We can only add or subtract like radicals. Now, you're probably familiar with the term like terms in algebra, and that's something we've been using for a while. In fact, we can only add or subtract like terms. So what is a like radical? That's a fair question. I'm going to use the notation of a radical or a root to list that out. So the number that you have in the root symbol, kind of like up in the wedge corner, that's called the index of a radical. So remember, if you do not see a number there, you assume it's a 2, which is a square root. Otherwise, you might see a number there like 3 or 4, indicating a third or fourth root. That's the index. And then what's underneath the actual radical sign is called the radicand. And for radical expressions to be like, then we must have both of them matching. So for like radicals, both match. And by both, I mean the index and the radicand. And so we're going to see this kind of played out with some examples here soon. I just wanted to make sure that definition was clear before we got started. Now, beyond that, we'll also use, we've discussed some radical expression properties already. We're going to remind ourselves of some of those. Namely, if I have the square, or the nth root, some n index value there, the nth root of a fraction a over b, then you can split up the fraction and take the nth root of the numerator and the nth root of the denominator. And we've seen that happen already, but I want to remind us of that. Now, let's try to simplify some radical expressions using these ideas. Our first example begins as 7 square root of 3 plus 2 square root of 3. And when you see a 7 written right out in front or to the left of a root, like we do here, or same thing with the 2 in the next term, then those are considered to be multiplying next to those roots. In other words, it's like 7 times the square root of 3 and 2 times the square root of 3. But if you look above at our little definition or diagram, the index is not the same as that number out front. Rather, that's called more like the coefficient. And so we're not talking about an index when we look at the 7 and the 2 there. Now, with that being the case, these two roots in this problem, in each expression, notice their index is not written. There's nothing written in the little wedge portion of the radical symbol, which means we assume it's a 2. These are square roots, and therefore they match in terms of the index. Also notice that the radicands, the numbers underneath the roots, are both 3, which means we have like radicals according to our definition above. So we can add like radicals, and we do so simply by adding up their coefficients. So, I mean, think back to the good old days. If you had 7x plus 2x, you would say, oh, that's 9x. You're just adding like terms. Well, in the same way, 7 square root of 3 plus 2 square root of 3 would simply be 9 square root of 3. And there's nothing else we can do beyond that to simplify or combine anything else, so we'll leave it right there. Let's go on to our next example. This one begins as 8 square root of 17 minus 5 square root of 19 minus 6 square root of 17 plus 4 square root of 19. So we have 4 different radical terms. Notice some of them are like and some are not. They're all square roots, given by the fact that there's no index number written. But notice the radicands are different in some cases. So you have the first and third terms both have a square root of 17, so those are like. And then the second and the fourth terms both have square root of 19, so those are like. So we'll simply combine the like terms. If you look at the root 17s, you have a positive 8 and a negative 6. Just like we would do with like terms, you keep the sign in front of a term with it. And so a positive 8 and a negative 6 combine to be a positive 2, and we keep the radical part with them, describing them. So 2 root 17 would be the combination of those 2 root 17 expressions. Moving on, we have negative 5 root 19 and positive 4 root 19. Well, again, combine those coefficients. A minus 5 and a plus 4 would be a minus 1. So you could just put minus square root of 19. You could sneak a 1 in front of that if you want to, but it's not necessary. You can just leave it like this. So now we have 2 root 17 minus root 19. Of course, those are not like radicals, so we cannot combine them any further, which means we stop right there. Our third example begins as 3 times the cube root of 24. Notice the index value of 3 indicating a cube root there. So 3 times the cube root of 24 plus the cube root of 81. Now at first glance, these are not like radicals. Now they do have the same index, they're both cube roots, but the radicands, that is what is underneath the roots, don't match. So either we're stuck and we can do nothing, or perhaps we should try to utilize some of the reducing tactics we've already done in previous topics. So we know how to reduce a radical by factoring it into numbers which have a factor that matches the index root. What I mean is this: if you take the cube root of 24, there actually is no nice number such that it cubed equals 24. However, as we've seen before, if we split this, instead of cube root of 24, I write it as the cube root of, and then I factor 24 as, say, 8 times 3. The reason we may be motivated to try that is because 8 actually is a perfect cube number, which means we should be able to reduce that, as we've seen done before. Okay, similarly with the next term, though 81 is not a perfect cube number, I should be able to factor it, so we're going to rewrite this as the cube root of, and then 81 happens to be 27 times 3. Now the reason that matters is, again, because 27 is a perfect cube number, which matters because we're taking a cube root here. So now if we go another step, we can reduce in the first term the cube root of 8. Now the 3 that was out in front as the coefficient stays out in front, but then when we reduce the cube root of 8, of course that is 2. So that 2 is going to come out in front with the 3, and it's going to be multiplied by it. And then the cube root of 3 is not reducible, so it's going to stay underneath the root, just as you see it. So we have 3 times 2 times the cube root of 3, getting to our simplified result. Of course, we'll multiply the 3 times 2 together in the next step, but for now, that's how we're going about this. In the next term, same idea. The cube root of 27 is really just 3, so we're going to put the 3 out in front as the coefficient now, and we're going to be left with a cube root of 3 that would not be reduced under that root. And so now, well, if we take this a step further, we really have 6 times the cube root of 3 in the first term, and then plus 3 times the cube root of 3 in the second term. Notice now we actually do have like radicals. So since that's the case, we'll go ahead and combine them by simply adding up their coefficients. 6 times the cube root of 3 plus 3 times the cube root of 3 would be 9 times the cube root of 3. So again, we're just adding up these coefficients. 6 plus 3 is 9. That's where that comes from. And of course, there's no way to reduce this any further, so 9 cube root of 3 is our final result. If we go on to our next example, this one begins as the square root of 4x minus 12, all of that being underneath the square root, plus, and then a different square root next to it, so plus the square root of x minus 3. Notice in this case, we do not have like radicals because these don't match entirely. Their indexes do. The fact that they're both empty means they're both 2 or square roots. So those match, but the radicands, that is what is underneath the roots, do not match. So we're going to have to try to reduce this a little bit before combining, as we did in the previous example. Notice in this first root, what is underneath the root, that is the radicand, is factorable. You could factor out a 4 from the 4x minus 12, which of course would leave you with an x minus 3 in parentheses, now with the 4 factored out in front of it, all of this being underneath that square root. The second term cannot be reduced. We'll just copy it down as the square root of x minus 3. Then notice there's a little bit more reducing we can do. If we pull out some of our root properties, when we have a product inside a radicand, or in other words, a product underneath a square root, as we do in this first term, we have 4 times the x minus 3. That's a product. According to our root properties, we can split up a root of a product, so we use the root of each factor. So really it's the square root of 4 times the square root of x minus 3, splitting up each of those factors from that previous step. We'll just copy down that last term of square root of x minus 3. There's nothing else we can do with it. But notice now we can reduce this square root of 4 that's way out in front. The square root of 4 is 2. So really we have 2 times the square root of x minus 3 plus the square root of x minus 3. Well, now we actually do have like radicals. Notice we have matching indices or indexes of 2. They're unwritten, so they're both square roots. And then the radicands, or what's underneath each root, match now as x minus 3. And so we're going to combine these like we've been doing. Notice that the coefficient of the second term is really an invisible 1. So you could write it there if you want, just to be clear on it. But ultimately, you're going to add up these like radicals to say 2 times this root plus 1 times this root would be 3 times this root. So 3 times the square root of the quantity x minus 3 is our final result. Let's go on to another example. This next one begins as 4 times the cube root of the quantity x to the 4th y squared. That's the first term. And then it's plus, the second term is 5x out in front times the cube root of the quantity xy squared. Now you'll notice right away that though these index values do match, they're both cube roots. What's underneath the roots, the radicands, do not match. So these are not like radicals, at least yet. But as we've been seeing, sometimes you can reduce them to get that set up for you. So let's try this first term, rewriting it as keep the 4 out front. But now underneath the cube root, instead of x to the 4th, we may be motivated to split that into x cubed times x. We've seen this done before. We're splitting up this power of 4 to make it into one power at least that is divisible by this root number, right? 3 divided by 3 works nicely, and when we're reducing terms in this next step, we would need to do that. So we're going to make this x cubed times x instead of x to the 4th, and then after it, we'll just keep the y squared. Okay, let's move on. The second term cannot be reduced. We're going to leave it as 5x times the cube root of xy squared. But then if we go back to that first term, notice the cube root of x cubed is really in the first spot underneath this radical. So we really have 4, that's out front as the coefficient, and then the cube root of x cubed is just x. So that gets reduced. Underneath the cube root, however, we will still have xy squared because those did not get reduced. If we copy down this original second term as 5x times the cube root of xy squared, notice now, finally, we have like radicals. And there's a lot to match up here. Notice they're both cube roots, so the index values match. What's underneath each root matches as xy squared, which means we have like radicals. But more than that, notice that what's out in front of each radical would be considered like terms, 4x and 5x. It's also required to have those match in terms of being like terms if we want to go further. So 4x plus 5x, of course, is 9x. Remember, we just add up the coefficients. And so we did that there. We have now 9x times the cube root of xy squared, which is how we combine these like radicals by adding up their coefficients. In this case, they were both x terms. And so 9x cube root of xy squared is our result. Our next example begins as a fifth root of a fraction. So underneath this fifth root in the fraction, okay, so the numerator is 64x to the 14th power, and the denominator is y to the 15th. Now we're trying to think ahead, knowing we're going to try to reduce this with a fifth root. To do so, we're going to have to split some things up like we've been seeing here. So if we rewrite this root, but then think ahead, notice in the numerator we have this 64 coefficient. Well, 64 is not a power of something to the fifth. So we're going to have to split it because we know a factor of it that is, actually. So let's rewrite this entire fifth root. I'm going to write a large fifth root. Now underneath it, in the numerator of this fraction, instead of 64, we're going to rewrite that as 32 times 2, because 32 happens to be 2 to the fifth power, which means it will reduce nicely with a fifth root. And we want that. Now we also have this x to the 14th up there. Remember, to reduce a power of a variable, we're going to be dividing the power by the root. but 14 does not divide by 5 nicely or cleanly. So we're going to have to do what we've done before with things, which is split up the power of x so that we use the next highest power below 14 that is divisible by 5 nicely. So that, of course, would be 10. So we're going to rewrite this as x to the 10th times x to the 4th. Of course, together those would be x to the 14th, but now we can at least reduce part of that. And then down below we have y to the 15th, but that power of 15 is already divisible by 5, so we're good there. All right, let's go ahead and take a step in the right direction of simplifying this here. In the numerator, we have the 5th root of 32. That's really just a 2. That's popping outside the root, and it's going to remain now up in the numerator. So let me put a fraction here for our answer. The 2 that we have here stands because it's the 5th root of 32. That was that first factor under the root. Beyond that, if we look down, of course, this is dangerous. Notice that my root got a little bit cut off. This should go all the way through, covering all the powers of x as well. Okay, so after reducing the 32 with the 5th root to get the 2, which we just did, we can move on down. 2 does not reduce, but x to the 10th would turn in. Remember, we divide the power by the root, so 10 divided by 5 is 2. So really, this is an x squared that would be popping out in front along with that 2 that we already had out there. Then if we move down the line, of course, x to the 4th can't be reduced. So we're left with some things underneath the 5th root that do not reduce, and that would be just the 2 and the x to the 4th. So we can leave that as 2x to the 4th under that 5th root. Now down below in the denominator, we can divide 15 by 5 nicely. That is dividing the power by the root. Okay, so 15 divided by 5 is 3, which means we simply have y cubed left in the denominator. And this is as good as we can get it right now. So we have in the numerator 2x squared, and then 5th root of 2x to the 4th, and that's all over the denominator of y cubed. Okay, our next example begins as a fraction of roots. The numerator has the square root of 54, a to the 7th, b to the 11th. That's all underneath that square root. And then the denominator is a square root of 3, a to the negative 4, b to the negative 2. Now there's a lot to look at in this example, and your eyes may be drawn to the fact that we have an a base on top and bottom, as well as a b base on top and bottom, and we're used to combining those so that we end up with one of each variable base. Now that is still where we're headed. However, since these are both stuck in their own square roots, we cannot just combine them. It's like these square roots are brick walls. We can't just bust through them to combine these, base A's or base B's. What we have to do is first utilize one of our properties of roots that we've been working with here for a while, and that is if you have the square root of a something over the square root of something else, one of the properties we have, actually we reviewed it way above here in our notes in this topic, is you can make the square root of the entire fraction. So put it all underneath one large square root. Since those roots match, that property works fine. So now underneath the square root, we have a fraction where we have 54 a to the 7th, b to the 11th in the numerator, and then 3 a to the negative 4, b to the negative 2 in the denominator. Now, since this fraction is all underneath one large square root, we can simplify the fraction underneath the root. So we can go ahead and do 54 divided by 3, which does happen to reduce to 18. And then we can combine these base a's. Of course, we'll bring the smaller to the larger. If I bring the a to the negative 4 up, I would combine it with the a to the 7th to get an a to the positive 11. And then similarly with the b's, if I bring the b squared up, then I would combine it with the b to the 11th that's up there and get b to the positive 13th. Now this is all still underneath the square root. We cannot forget that. So we've reduced the fraction that's underneath the square root, but now we have something that maybe we could reduce further. Notice the first factor underneath the square root is 18. Though that's not a perfect square number, we could factor it using 1. So really 18 is 9 times 2, and of course 9 reduces with the square root, so that's good news. We're dividing powers by roots here. The index is unwritten, so it's 2 as a square root. 11 does not divide by 2 nicely, so we're going to split that to be a to the 10th times a, because 10 is the next lowest number that does divide by 2 nicely. And then lastly, the b to the 13th in similar fashion will make b to the 12th times b, because we can divide 12 by 2 nicely. So now let's go ahead and wrap this up with a reduced answer. The square root of 9 is 3, so that gets reduced. 2 stays, can't reduce it. The a to the 10th, we divide the 10 by 2 to get a to the 5th, so that got reduced. The single a following it stays, but then the b to the 12th, we divide the 12 by 2 to get 6, so we have b to the 6th, that got reduced. And then the b at the very end will stay as well. So underneath the square root, at the end, we have anything that did not get reduced, which would include the 2, the single a, and the single b. So altogether we have 3a to the 5th, b to the 6th, as the coefficient out in front of this square root of 2ab. And that's where we're going to have to stop for this final answer. Our next example begins as a fraction of radicals. This time the numerator is the cube root of 250 x to the 5th y cubed. And then the denominator is the cube root of 2x cubed. Well, kind of like we just did in the last example, we can start right away by using a root property to kind of blend these all into one big root. Remember, we're kind of locked in these roots, and though we might want to simplify some of these things in the numerator and denominator, we cannot unless we have them all under one large root. So in this case, we're going to use the property and turn this into a large cube root, where the numerator will contain what we had in the numerator previously, so 250 x to the 5th y cubed, and the denominator will have 2x cubed. Now, again, the motivation to do this is that now we're allowed to reduce what's inside the radical, and there is certainly some things we could reduce in there. So we have 250 divided by 2. We'll go ahead and just do the arithmetic reducing there. That happens to be 125. After that, we have x to the 5th over x cubed. Well, that's really just x squared. And then we have y cubed kind of on its own there at the end, which we'll bring down as well. Now, the cube root of 125, that does reduce to 5. The cube root of x squared does not reduce, so we'll just leave that one alone. And then the cube root of y cubed, that does reduce. You can divide 3 by 3 to get y to the 1, or just y. So really we have now 5y times, there's still left the cube root of x squared because we couldn't reduce that one, but that's where we can stop. Our next example begins with a fraction of cube roots. So in the numerator of this fraction, we have the cube root of, and then underneath the cube root is a cubed minus b cubed. Down in the denominator, we have the cube root of a minus b. Now, at first glance, you may be thinking, oh, we've seen this kind of thing before. We can go ahead and turn these two roots into one large root and then try to factor. Okay, sure. So we've been doing this. We know that we're kind of stuck inside these cube roots individually, top and bottom. So if we blend this into one large cube root, like we've been doing in examples above, then we could write this as a cubed minus b cubed in the numerator over a minus b in the denominator, all of this being underneath a large cube root. Now, as far as reducing something like this, you'll recall with subtraction signs like we see here, we cannot simply combine the base a's and base b's by bringing stuff up and down and adding or subtracting exponents, not when you have subtraction really or addition gluing things together. So rather, what we're going to have to do in this one is rewrite the expression, except realize that the numerator is actually a difference of two cubes. So you may recall from factoring, a cubed minus b cubed is really just a minus b in parentheses times, following it, we have a squared plus ab plus b squared. Okay, so that from numerator to numerator there, that is a difference of two cubes. Sometimes DOTC is used as an abbreviation for that. Difference of two cubes. It's just a factoring strategy. And then we'll leave the a minus b alone that we had in that denominator originally there in that previous step. But now you'll notice the whole point of this is that we can actually spot some matching factors. We have an a minus b and an a minus b top and bottom, which means we should be able to cancel those out and be left with this large cube root under which we have a squared plus AB plus B squared, really just coming from the second factor of that difference of two squares that we had previously. Now this, where we stand now, is not possible to reduce. Remember, you cannot go through and try to take the cube root of term by term with addition or subtraction separating things. You cannot split up terms with a root. And so we're going to stop right there where we are. That's our final answer. Now in this next example, let's see, it begins with a term out front, which is 7 times the square root of 2x cubed. Then we have a plus sign, and then we have a fractional term where the numerator is 40x cubed times the square root of 150x squared. And then underneath that, in the denominator, we have 5x squared times the square root of 3x. Now, let me just kind of start off the bat on this one by saying it's possible to go a couple different routes on a problem like this. For instance, some people may be inclined to say, oh, I'm going to get a common denominator right away. Okay, you actually could do that. That's fine. I'm probably going to choose a slightly different route, but I just want to make it clear that it's not that there's only one way to get through a problem like this one, or really many of these. So let's go ahead and take this one by looking at the second term, which was the fractional term originally, and seeing if we can find ways to reduce what we see there. So I'm just going to copy down the first term as 7 square root of 2x cubed, then put the plus sign, and then for the fractional term, let's do some reducing as we see it. So notice we have a 40 over a 5. That would reduce to simply 8. And then we have this x cubed over x squared. Those reduce to just an x. So really we have 8x so far. But then we have the square root of 150x squared over the square root of 3x. You'll recall we could turn that into, maybe I'll write this out as an extra step here. We're going to turn that into one large root, where the numerator underneath the root would be 150x squared, and that would be over 3x. All of that being underneath this big square root. Now, if we continue on, let's copy down again this first term as 7 square root of 2x cubed plus, and then we have our 8x coefficient from our step before it. But then we have underneath this root in the fraction, 150 divided by 3, of course, that is 50. So we're going to put this as the square root of 50, and then x squared over x would be just x. We may spot at this point a way to go further with these terms, so let's do that. And by the way, if you had spotted to do this earlier in the first original term, that would have been fine. But what I'm saying here is that we can reduce this original first term root. It was the square root of 2x cubed. Well, x cubed can't be reduced by a square root, but we know how to split and reduce that by now, so we're going to do that. I'm going to leave this as 7 times the square root of 2x squared times x. So x squared x is underneath the root now in place of the x cubed. We'll be able to reduce that x squared. On to the next term, I'll put plus, and then I'll keep the 8x coefficient we have out there. And then underneath this root, we had 50 times x, so we had square root of 50x. But let's split up that 50 as 25 times 2, because actually that works as factors of 50, and we're motivated because 25 is a perfect square number, which means we should be able to reduce that as well. So let's go ahead and reduce again another time here. We have the 7 out in front of our first term. Then the x squared underneath the square root is going to get reduced and pop out as just an x. So really we have 7x out in front, and then we have the square root of 2x after it. On to the next term, we're going to keep our 8x out in front. However, notice that underneath the root we have this 25. The square root of 25 is 5. When that 5 pops out, really it's going to be then 8 times 5, which of course is 40. I'm just going to write that now. So we'll say 40x. No, actually I'm going to write that out as one step at a time. So we had the 8x out front, but then we're going to multiply it by a 5 because that 25 will get reduced underneath the square root as that. And then we're left with the square root of 2x. Okay, let's keep going. So we now have 7x square root of 2x plus, if we multiply what's in front of this next root together, 8x times 5 would give us 40x, and then that's times the square root of 2x. Notice at this point we have like radicals and like terms in front of them, so we can combine these. 7x plus 40x would be 47x times the square root of 2x. And that's one way we could leave it to stop. Again, if you had gone a different route and maybe gotten a common denominator for this one, your answer might end up slightly different, but this would be a nice clean way to simplify this example. All right, lastly within this topic here, we're going to recall first of all the domain for radical expressions or functions. We've seen this previously, but I'm bringing it back in here to just remember. Actually, domain in general, as we've seen it with various types of functions. Remember, we've done rational functions and radical functions at this point, and because of that, our domain has two considerations. First, we cannot divide by 0. Now, that's more of a rational expression consideration. But secondly, we cannot take the even root of a negative. Now, that's more of a radical expression consideration, and we've seen both of those things happen already. We're just going to kind of bring them back into play here to review. So let's now try to find, in this next example, f over g of x, so that's a quotient of functions, and its domain, where we're given f of x equals the square root of the quantity x squared minus 25, and then g of x is equal to the square root of the quantity x plus 5. Now, you'll recall, given what we know of functions, that f over g of x, that notation simply means f of x over g of x. So we're going to simply put the f function over the g function, which when written would look like the square root of x squared minus 25, that's the f function as given, and then that's in the numerator. Underneath it, in the denominator, we'll simply have the square root of x plus 5. That's our g function as given as well. Now, we want to find and reduce this, but then also, as mentioned here, find its domain. You may recall that there is a way to go a little bit further in simplifying this. So we could perhaps factor the numerator and also combine something we did above, which is put this quotient of roots as one large root. So instead of a square root in the numerator and denominator separately, we can make this one large square root, where in the numerator underneath it we have x squared minus 25, and down below we have x plus 5. So that's just a root property or radical property there. Now let's keep that going, because this is where we're going to pull in some factoring. So that numerator of x squared minus 25, you may recall that's a difference of two squares. We could write that as x plus 5 times x minus 5. Of course, the x plus 5 already sits down in the denominator below it. And then we can reduce by canceling the matching factors of x plus 5. So we'll cancel those out, which will leave us with simply the square root of x minus 5. Now, to consider the domain of this expression, we need to recall our rules above. We cannot take the even root of a negative. Well, this expression where we finished has a square root of x minus 5, which means what's underneath that square root cannot be negative, which means, as we've seen previously, x minus 5, that's what's under the root, that has to be greater than or equal to 0. That would mean non-negative. So we solve this simple inequality here by adding 5 to both sides. That would give us x on the left side is greater than or equal to a positive 5, just by adding 5 to both sides. So altogether, if we use interval notation, we could say our domain is 5 to infinity with a bracket on 5, because we have x has to be greater than or equal to 5 here. And so our domain of this final simplified function above is 5 to infinity with a bracket on 5.